Okay, so in the previous video, we introduced the idea of this precise definition for the limit. Now, we haven't used that definition to prove any limits yet, but we have sort of established it and worked with that idea a bit. So before we get into a full-on proof, which is kind of an involved process, I want to take a look at an example that you'll see in the homework, or you'll see homework problems like this one. So it says, using the graph of f shown below, right here, determine the value of delta such that if the absolute value of x minus 3 is greater than 0 but less than delta, then the absolute value of f of x minus 2 is less than 0.5. And remember, we're using the precise definition of a limit here to sort of interpret what these different values mean. So remember, looking here first, f of x minus 2 is less than 0.5. This is suggesting that the limit of f of x, whatever f of x happens to be, we know we have a curve here, but we don't know what the function looks like algebraically speaking. Whatever f of x is, the limit as x approaches 3 is going to equal 2, or at least that's what they're suggesting with the values that we're getting here. And then this number here, remember I was calling this a threshold in the previous video. This is like our value epsilon. Remember, what this does is it determines how far f of x can get from 2 under this constraint right here. So looking at our graph, you'll notice 2 on my y-axis appears right here. And then we have 1.5 and 2.5 where we've drawn these red lines. Notice that these two values are exactly 0.5 away from 2. So this thing right here, in the last video we said determines an interval, and this is that interval right here. It's the interval centered at 2 with a distance of 0.5 from its endpoints. This delta here also determines an interval, but it's going to be an interval on the x-axis as opposed to the y-axis. That interval will be centered at 3, which is why we're seeing 3 here. And the distance to either endpoint of that interval is going to be whatever this delta is. Okay, so where did these values here come from? Well, these values are what would have to be plugged into our function to give us the endpoints of this interval. 2.6 when plugged into f gives me 1.5, and f of 3.8 looks like will give me 2.5. Okay, notice that the function doesn't have the curve doesn't have a point here. There's an open circle, and the point lies outside of this little rectangle, or this little region that we've created out of these red lines. This is where this little condition is important. Because remember, this greater than 0 here implies that 3 does not have to belong to the interval that we're looking for down here, which is why we're getting a point out here. It doesn't matter that that point is out there. But anyways, the goal here is to select a value of delta, which would create an interval around our number 3 here on the x-axis, such that all of the x values in that interval, when plugged into my function, give me y values that are inside this strip right here. Okay, it's like what we saw up here in the previous video. So the trick here is to look at these two endpoints, the 2.6 and the 3.8, and pick whichever one is closer to 3. Visually, I can see that 2.6 is closer, and specifically, what is the distance from 2.6 to 3? I could use that distance formula that I came up with at the beginning of this section, or it's pretty easy just to see that it's 0.4. What would happen if I went 0.4 in the other direction, though? If I went another 0.4 this direction, that would take me to 3.4, which gives me this little guy right here. Now notice, if I do this, if I create this little strip using that interval that I just found, any point within that interval when I plug it in is going to take me, or any number in that interval when I plug it in will take me to a point on my curve that is inside that horizontal strip that we created. Okay, if I pick that value it takes me to this part of the curve, which is inside that strip. So by choosing the smaller of the two distances from 3, I get a small enough interval so that it does what it's supposed to do. This suggests that 0.4 is what I want delta to equal. Okay, so I'm going to say delta equals 0.4. And notice I could have made delta even smaller. If I made delta equal to 0.1, I would have gotten a very, very small interval, which would have done the same thing. But the graph is suggesting a value of delta that's equal to 0.4. Okay? All right. So now we're going to get into our first actual proof of a limit. And what I want to do here is go back to my precise definition just as a reminder of what we're looking for. Okay, so here's our precise definition, and this one, they tell us what the limit is. The limit as x approaches -6 of this linear function 1/3 x plus 5 equals 3. So keeping those values in mind, we want to use our definition. If x minus -6, so I could also say x plus 6 in that case, is greater than 0 but less than delta in absolute value, then f of x minus 3 is less than epsilon, where up here we had chosen some arbitrary positive number epsilon and found a corresponding delta, which is also positive, that makes this true. So when we do these proofs, what we're generally going to be doing is some preliminary work before actually writing up the proof. And the preliminary work is kind of like working backwards, okay? So preliminary, I'm just going to say preliminary work. Like that. Okay, so the way the preliminary work is going to go is we're going to go back to my definition here really quick. We're going to start with this guy. We're going to pick some arbitrary number epsilon and then try to do some algebraic work to determine what the corresponding delta should be. And we kind of already did this with that example in the previous video, so it'll look kind of similar. Here's what we want. We want my function f of x, which looks like this, 1/3 x plus 5, minus the limit, which is 3, to be less than this number, epsilon. Okay? But now what I want to do, let me add this too. Whenever this is true. Okay? So that's kind of saying what the precise definition is telling us. So what I want to do is kind of work with this side, and my goal is to try and make something that looks like this appear in my simplification here. So working with this guy, if this is less than epsilon, then I have this, 1/3 x. Simplifying this, 5 minus 3 is 2, so I get plus 2. What if I factor a 1/3 out? Well, as we've seen before, you can pull a 1/3 out and just make sure you take its absolute value as you do, which would still be 1/3. This is equal to 1/3 x plus, if you factor in 1/3 from 2, you get 6. Okay? So if this is true, then by simplifying it, we must also have this being true. But notice this x plus 6 in absolute value resembles the thing that I'm looking at over here. I'm going to use it to find this delta. So I need the absolute value of x plus 6 to be less than some constant here. And I almost have that. I have 1/3 times x plus 6 is less than delta. So I can multiply both sides of this inequality here by 3 to get this. X plus 6 is less than 3 epsilon. Okay? This thing right here is what we're going to set delta equal to, and it reveals something about these problems. When we're doing a proof, one of these epsilon delta proofs, because we don't know what epsilon is equal to. We're kind of picking an arbitrary epsilon and we're not assigning a specific value to it. Delta is not usually going to come out to some specific constant. It's going to depend on epsilon somehow. So this thing, this 3 epsilon, is what we're going to be setting delta equal to. Okay? So this is the preliminary work. This is not the proof, but we use this to determine what delta should be, and then we write the proof. Okay, so I'm going to go down here and say proof. So for my proof, let's look at the definition one more time, and let's see what we would need to state first. It says, if for every number epsilon greater than 0, there is a number delta greater than 0, such that if this, then this, then our conclusion would be that we have the limit that we're looking for. So what we have to do is start with that epsilon. We're going to say, let epsilon be greater than 0. You always start these proofs with that exact statement, because what you're doing is you're now identifying epsilon as some positive number, and now you can work with it in some way. We're going to say, let epsilon be greater than 0, and we're going to set delta equal to 3 epsilon. Okay? So this is using the result of our preliminary work right away. Now what we want to do, again, let's go back to the definition, is prove this if-then statement. Now anytime you want to prove an if-then statement, you assume the if and then use some kind of logical steps or algebraic steps to arrive at this conclusion. We would call this a premise and this a conclusion. So I'm going to say assume that this is true. I'm going to say assume that 0 is less than the absolute value of x. Now remember, where x is approaching -6 here, so x minus -6, which is the same thing as x plus 6, and that's less than delta. The goal here is to show that this is true. Okay, so I'm going to basically work these steps backwards in a certain sense to get back to here. Then, so let's write this out. The absolute value of this guy, 1/3 x plus 5 minus 3. And what we're doing now is a little bit of algebraic work. This is equal to the absolute value of 1/3 x plus 2. Doing the same factoring that we did before, we could pull a 1/3 out, which is equal to 1/3 times the absolute value of x plus 6. And this step is where we use this assumption. So we have assumed that the absolute value of x plus 6 is always less than delta. Using that here, this would say that this is less than 1/3 delta. Okay, because I have this 1/3 out here. But what is delta equal to? Well, delta, we set up here, was equal to 3 epsilon. And you notice what happens? I get cancellation here. And what have we done? Well, we've proven what we wanted to prove. We have shown that the absolute value of our function minus the thing that we're saying is the limit is less than epsilon. That's the proof that we were looking for. So we can say, therefore, if you remember, these 3 dots in a triangle mean therefore, the limit as x approaches -6 of 1/3 x plus 5 equals 3. Period. I would recommend going back over this proof a few times, because this is a notoriously tricky subject to get used to. But this is what these proofs look like. And again, remember, we typically always start with this preliminary work and then use it right here in the beginning. We're using the work that we did to set delta equal to something in terms of epsilon, and then write up our proof this way. Okay? Let's try a different one. This one has a little bit more intricacies to it. So again, we're looking at a limit. This time x is approaching 2 of x squared, and we're going to say we want to prove that it's equal to 4. Now, we already know that it's equal to 4 because you can evaluate that limit using direct substitution. We've done much harder limits than this one using our limit laws. But the goal here is not just to know how to evaluate it. It's to prove that it's true without just assuming that the limit laws work just because we said they did. So again, we start with this preliminary work. Okay. And just like before, what we want, I'll go back here and show you how we started this again. We want this to be true whenever this is true. So in our case, we want the absolute value of our function minus our limit, so that's x squared minus 4, to be less than epsilon whenever this is true. X minus 2 is less than delta. Okay? And remember, the goal of the preliminary work is to determine what delta is in terms of epsilon, so that this implies this. Okay? And remember what we did before is we took this inequality and we tried to play around with the absolute value here until we got something that looked like this. Okay, so what I'm going to do is factor this. I have x squared minus 4 in absolute value, which is equal to x minus, I'm going to say x plus 2, x minus 2. And we know that this is less than epsilon, or we know that we want to make it less than epsilon by choosing the appropriate delta. So I'm seeing an x minus 2 in absolute value here, and remember that's kind of what we were trying to make appear somehow. But where this guy differs from the previous problem is that when I did my preliminary work before, I had a constant times the expression I was looking for. That's not the case anymore. I have an expression in terms of x multiplied by the expression I'm looking for. And I have to be exceptionally careful with this because this quantity can change depending on what I choose for x. So it would help if I knew that this thing was bounded in some way. So what I'm going to do is this. Suppose the absolute value of x plus 2 is less than c for some constant c. I want to figure out what c would have to be to do this, because what that's going to allow me to do, as we'll see in our work, is it's going to allow me to replace this x plus 2 with that c to create sort of an upper bound here. Now, to do that, I want to work with this guy, because remember, when we do this proof, we're going to find a delta and we're going to assume that this is true. Okay? Now, remember also that the idea behind a limit is that x is approaching 2. So we're going to be assuming that this absolute value is relatively small in the back of our minds. That's kind of how we're thinking about it. What I'm going to do is just put an arbitrary bound on this for a second. Suppose, Suppose the absolute value of x minus 2 is less than 1. I'm choosing 1 arbitrarily, but I'm choosing it specifically because it's a small number. Okay? Based on what we've seen before, this is the same thing as saying that negative 1 is less than x minus 2, which is less than positive 1. Or if I add 2 to everything, 1 is less than... Actually, sorry, I don't want to add 2. I would like the thing in here to look like a positive 2. Okay, so what I'm going to do is add 4 to everything. That becomes 3. X minus 2 plus 4 would become x plus 2. 1 plus 4 is 5. Now, what was the point of that? Well, if x plus 2 is less than 5, then the same is true of its absolute value. 5 is positive, so I can't take an absolute value of this if it's already less than 5 and greater than 3 well, let me back that up. If x plus 2 is between 3 and 5, we already know that it's positive. So the absolute value of x plus 2 is going to be the same thing as x plus 2, which would also be less than 5. So I have this. X plus 2 is less than 5. Okay? Notice we wanted a constant that was kind of like an upper bound on this absolute value. And right here, I've located that constant. Okay? So that's the thing that I'm going to be calling C. Now, if I do that, if I've assumed that delta is at least as small as 1, then I can replace this x plus 2 in absolute value with a 5 here. So x plus 2 times x minus 2 would be less than 5 times absolute value of x minus 2. Notice this is true because I've changed this x plus 2 into something that's larger than it. So this would be larger than this. And I want that to be less than epsilon, which implies that the absolute value of x minus 2 is less than epsilon over 5. I just divided both sides by 5 right here. So notice now, in order to make all of this work, I have two conditions that I've put on the absolute value of x minus 2. Depending on what epsilon, regardless of what epsilon is, I need x minus 2 to be both less than 1 and also less than epsilon over 5 at the same time. So notice if epsilon is a small number, like 2, then saying that x minus 2 is less than epsilon over 5 is going to give me less than 2/5, which is already less than 1. So it's already satisfying both of those simultaneously. If epsilon is a really big number, like 100, then if I assume that x minus 2 in absolute value is less than 1, it'll automatically be smaller than this bigger number also. So what we do is we set delta equal to this. And this is probably notation you have not seen before, so I'm going to explain what it means. This notation means the smallest of these two numbers, min, as in minimum. So remember that we're choosing epsilon arbitrarily, so depending on our choice of epsilon, 1 might be the smallest of these two numbers, or epsilon over 5 might be the smallest of these two numbers. But we set delta equal to whichever one is the smallest. Okay? After all that preliminary work, we're ready for a proof now. Okay, so remember how we start our proofs. We always write let epsilon be greater than 0. And then we use our preliminary work to come up with the next statement. Set delta equal to the minimum of 1 and epsilon over 5. Okay? And now what we're going to do is make the assumption that's in the premise of the statement of our precise definition. So I'm going to say assume 0 is less than the absolute value of x minus 2, which is less than delta. Okay? And now what I want to do is start working with this guy up here, this x squared minus 4. But before I do that, I'm anticipating what's coming because I've already done some work with this guy and I've seen that this absolute value of x plus 2 is going to end up showing up somewhere. Okay? So what I'm going to do is basically do what I've done here, where I break this up and try to into a compound inequality and try to make an x plus 2 appear. So I can say something like this. Then I can say that the x minus 2 in absolute value is less than 1. And how do I know that? Well, if delta is the minimum of these two values, if it's equal to 1, then I can just substitute a 1 in there and I get this. If instead it's equal to this guy, then if this is less than epsilon over 5, it would have to also be less than 1 because this, by definition, it would be the smaller of these two numbers. So regardless of which one of these is smaller, this statement always allows me to say that x minus 2 in absolute value is less than 1. So I have this, -1 is less than x minus 2, which is less than 1. Or if I add 4 to all three sides like I did before, I get this, x plus 2, which is less than 5. Thus, remember, x plus 2 being in between two positive numbers implies that it's positive, so that the absolute value of x plus 2 is the same thing as x plus 2. And I can use this part of my inequality to say that the absolute value of x plus 2 would have to be less than 5. Okay, I needed to state that because I'm going to use this fact in this final stretch of my proof. So now we're going to set up the final statement of this thing. The absolute value of my function, which is x squared, minus my proposed limit, which is 4, is equal to the absolute value of x plus 2 times the absolute value of x minus 2. All I've done there is factor. Here, we made a statement that this x plus 2 in absolute value is always less than 5. So I can replace that with a 5, and now I get my less than symbol in there. 5 times the absolute value of x minus 2. Now up here, we said that we were supposing that the absolute value of x minus 2 is less than delta, which, like we said before, implies that it's less than both of these numbers. Specifically, it's also less than epsilon over 5, whatever epsilon happens to be. So this is less than 5 times epsilon over 5, and here's where we get that cancellation. 5 times epsilon over 5 is just epsilon. That's what I wanted to show. The absolute value of f of x minus my limit 4 is less than epsilon. Okay, so now I can state my conclusion. Therefore, the limit as x approaches 2 of x squared equals 4. Okay? I'm going to stop this video in just a second, but I just want to reiterate, this is a very, very tricky process to get your mind around, especially since you don't really spend much time working with proofs in classes that come before this one. So really take the time to digest everything that happened here, because it's a lot. It's a lot. I think we will be finishing up this section in the next video.